So this is the agenda I wanted to cover today. In addition to, I wanted to start with what Randy was talking about, and I will. It's why do we, with the delivery times, the lead times now for power transformers and even distribution transformers extending out to, at times I've heard already 10 years, depending on what you're buying and from whom and where. How are we, and you have problems with your transformers, how can you mitigate this and make these things live longer until you get a new one coming in? So we're going to cover here the why and the what to monitor a transformer. We're looking at the vital components, things that fail more frequently, and really carry on from there. So how do I advance this? Oh, there we go. So to begin with, when we look at the questions why, the biggest question, and before monitoring, we have to ask ourselves the questions why. And in this case, what the big question is, I have assets, I need to keep them living as longer than I would normally want to do the replacement of them. And how do I go about doing that? So answer it. That's the answer. A life extension, call it that. And who is impacted? Well, it's going to be the people involved in maintaining the system and the reliability and the safety. And what is it going to be? What do I monitor on these pieces of equipment, and where and when? These are basic questions. So why? The biggest one is to reduce the risk of an unexpected failure. Generally speaking, the failure rate on transformers is low. LSMIEEE recently published a new guide on the transformer survey, as we call it, over a 10-year period, and summed it up with the people that participated, that failure rate is still around 1% per year of the, and that's total failure of the transformer. Here's the words from an insurance company, FM Global. This is from FM Global in Australia. And the focus should be not necessarily on cost as the previous cost of the asset itself. It's about the risk. And the risk is the consequences multiplied by the probability. That's risk. It's how do we assess the risk? And how do we reduce the risk? In other words, reduce the probability of something happening to reduce the risk. Out of the transformers, out of the worldwide population of transformers, this company insures about plants, substations and plants that total up around 100,000 transformers around the world, and 1,345 generating stations. The majority of the losses that they paid out in over that 10-year period was $937 million in gross losses, not including lost production time. The 554 failures were lasted over the 10-year period. And it's interesting, one footnote that they said bushings accounted for 8% of the total number of failures. So out of the 554 failures, 45 failures were associated with one bushing on a transformer failing and taking the rest of the transformer with it. And the cost of the failure due to that number of bushing failures represented $112 million out of the total of 937 million. But there's thing here is that the majority of these losses are preventable by increasing of the monitoring, by increasing of diagnostic testing and increasing of monitoring to let you know when things begin to go wrong. So who can be impacted? It's the, and these are the time for this comes from a LSMIEEE technical brochure number 630. This is the technical brochure. I participated in this one, and it's the one that defines the, I'll call it I won't call it the Bible. It's the guide to help you understand monitoring a transformer and what can be done. And it identifies who is impacted. And the primary users from an immediate, medium, and long term. These are the people who are interested to keep this transformer, keep the transformer in good condition. And the required outcome on the right-hand side, and first off, is always safety, continuity of supply, and the reliability of the system. That's the outcome that they want. The medium term is the maintenance, in other words, going into a planned maintenance rather than scramble. And with regard to the maintenance needs and the short-term replacement. Well, the short-term replacement these days is kind of hard to come up with because of the lead time so long. And longer term, this is where people are paying a lot of attention. How can I make this thing last longer to fit in with the long lead times for power transformers that exist today? So we talk about monitoring and and this is can be applied this to motors, to switchgear, to breakers, to transformers. This is the principle of monitoring versus diagnostics. This information comes out of a brochure that was published by Seagray, number 227, which is the life management techniques for power transformers. And you can apply it to just about anything. The point of monitoring, in this case, continuous online monitoring, is to answer the question, is it behaving normally? Yes or no? 90% of the time, yes, the answer is yes. So if you do nothing, you just keep in that circle and keep asking the question or reviewing the data, is it behaving normally, yes or no? 10% of the time, it's not. And that's now the question is how serious is this? And that's where diagnostics come to play. That's where you go and to the unit with test equipment, things like Drew was talking about, and assess the condition of the transformer. How serious is this issue? 8% of the time, it's not that serious. In other words, it may be serious, but you can fix it while there. It could be a bad bushing. It could be a problem with a tap changer. It could be an issue with the oil. You need to dry the darn thing out better than it is. And then once you're done, you put it back on the circle, asking the question, is it normal? 2% of the time, something is serious, and that's where the maintenance and repair, and in other words, you have to move the thing off-site to be fixed. Some units can be fixed on site depending on the situation, but if it's beyond that, you have to do it back in a factory. So monitoring can be looked at as a broadband technique applied on a routine basis. It can be a combination of continuous online monitoring and periodic testing of equipment. The diagnostic is what we call the focus technique, and you apply it as and when required, based on the answer to the question, is it normal, yes or no? And maintenance and repair, that's the time when in that 2% of cases, it needs, I call it sometimes major surgery to correct the issue. So transformer has many subsystems, and a failure in any one of them can cause a unit to trip offline. And most believe that the condition of a transformer is only as good as its worst performing subsystem and or component. That comes out of this brochure TB630. So consider that. You have a large transformer, it could be small or a large one. If you have a bushing, one bushing out of the 7 or 8, 9 or 12 bushings on the transformer, that is showing signs of a defect of imminent failure, the transformer is going to fail. So it classifies that whole transformer as in serious condition due to one bushing going bad. That's the point here. But there are essential subsystems to every transformer, and this is the diagram. The active part, the core and the windings inside the transformer, as we call it, the active part. You have oil preservation systems. The cooling system is vital. All of these things are vital. Bushings, and if the transformer is equipped with an on-load tap changer. These are the 5 primary subsystems on the transformer. So why and what to monitor? And I've been asked this question lots of times, and to me, the primary thing to watch are temperatures. The top oil temperature of any transformer, the bottom oil temperature, perhaps the winding hottest spot temperature on units greater than 2.5 MVA. And the ambient temperature is needed as a measurement because to perform a reliability check on the other 2 measures above. And in times, the ambient temperature can serve as a proxy for the bottom oil temperature of the transformer. Well, why temperatures? Because temperature affects everything on the operation of the transformer. If it's too high, the impact is advanced degradation of the oil and solid insulation if that's left unchecked. Winding insulation is very sensitive to temperature and moisture held by the paper. And this whole temperature measurement is an input to what I call input to other models to have a deeper understanding of the transformer's operation and behavior. It starts with this. Now, some of you I know will recognize this gauge on the side of the transformer. This is what's known as the winding temperature indicator or winding temperature simulator. This is technology from the 1940s when this was introduced. And essentially, it's attached to the transformer. You can see the drawing on the right-hand side. It's located in a well, dry well, welded to the side of the tank, and it consists of a couple of things. One of them is that dry well. There is a heating coil inside and a resistor, and that is meant to simulate the current flowing through the windings of the transformer. So this is a piece, this adjustable resistor is calibrated at the factory when the transformer is built so that you have a reasonable assessment of the winding temperature indicator as the load changes on the transformer and as the top oil temperature therefore changes as a function of load or ambient. So the other thing that most people these days have forgotten about this device is that this item needs maintenance. Or if you read the manuals for these things, it says this thing needs to have its calibration verified once every 4 to 5 years. If it's not, it can show signs of becoming stuck, out of calibration. It can seize up because of moisture getting inside and gumming up the works inside. It is a mechanical device after all, partly mechanical device, and it affects the accuracy of the device itself. Understand as well, this device is used to control the cooling system of the transformer. It's used to control the on and off of the fans and or pumps or in combination of the transformer. If this doesn't work correctly, your cooling system is not working correctly, which has the impact of increasing the temperature to a point where that transformer is going to age a whole lot faster than it was designed to. Here's an example. This was caught by one of our technicians on a new transformer that had been delivered in service for 3 months. And on the left-hand side, you see that's the winding temperature indicator. The red needle is indicating a temperature of about 50 or so degrees C. The right-hand side is the top oil temperature indicator, and it's indicating a temperature somewhere just about of 55 or pushing 60 degrees C. Now, this is an impossible situation. It's physically impossible to have the winding temperature indicator reading less than the top oil temperature indicator. Physically impossible. It goes back to this case. In this case, that winding temperature indicator was not properly calibrated in the factory. This transformer was only in service for 3 months. It was not done properly. So it was certainly not accurate. It wasn't because it wasn't set up like that. And the reliability of it to control the cooling system was compromised. So this is why we need these analog devices, I call them analog still, need to have attention paid to them. One thing in my travels around the world, when I walk into a substation and I start looking at transformers in the substation, these are the first things I look at to understand if these gauges are working correctly. And if they're not, I point it out to the people I'm with. I'm saying, whatever the situation is, this winding temperature indicator you have here has not, when was it last calibrated or had its calibration verified? And they look at me and say, well, what do you mean? You know, like, what are you talking about? I inform them that, hey, this thing can go out of the calibration over time. That's why you need to check it. And then they ask, well, how do I do that? And that leads into a whole nother discussion. Now, here's an example of what can go wrong. This is from a paper that was published. This is public information. This is on an older transformer. You can tell by the aging of these gauges. On the left-hand side, the top oil temperature indicator, and on the right-hand side, winding temperature indicator. And you'll note the winding temperature indicator drag hand, which is the red needle is about 65 degrees C, while the top oil temperature drag hand on the left-hand side, you can see is pushing at 110 degrees C. Stage 1 fans were set to come on at 75 degrees C, according to the winding temperature indicator. It never happened. So this says it's telling you the winding temperature indicator is non-functional. It's not working as it should be. Top oil temperature indicator is, but there's no alarm contacts on that top oil temperature indicator. All the alarm contacts and control the cooling system are coming from the winding temperature indicator. What was the result of this? Well, here's the record. They were sending people in once a month to go around and write down all the readings on the gauges on the equipment, on the tap changer, how, the spread of the tap changer, how many operations it's had, things of this nature, and top oil temperature and hotspot temperature as recorded, as indicated by the gauges. And here you can see over 8 out of the 12 months or so of this transformer, a little more than 12 months, that the top oil temperature indicator was reading more than the hotspot temperature. The person writing it down was not aware that that's a physical impossibility. Just dutifully wrote down all the numbers and handed it in, and this was a record of the entries into the CMMS system they had. It was reviewed, supposed to have been reviewed by people that know what they're doing. Obviously not. And out of that, this is what happened. That winding temperature indicator had seized. There was no cooling control, no alarms were issued. This transformer faulted in the right-hand side where you see the tubes. Those tubes were carrying two leads from 2 phases. That's common practice at that time. They were paper insulated and it's filled with oil. But the point is, there was all of this overheating in there without the extra cooling, had generated moisture from degradation of the paper to the point where in this transformer, it bubbled. Water vapor bubbled coming out of the paper insulation between phases, immediate turn failure, and did not catch fire, fortunately, but you can see on the left-hand side the damage, and it spread 20,000 liters of oil across the substation yard. That's the impact of a faulty temperature indicator, in this case, taking out the transformer. Another case where you can monitor the transformer with an electronic temperature indicator. Here's a case where on the left-hand side is data from the SCADA system. This happened in January 2010 in Appalachia, up in the mountains in Appalachia. And they received an alarm from this substation that phase A, according to the electronic monitor that was on it, it had reached a hotspot temperature of 143 degrees C. That's not good. They go out to site and they find there's only one single cooling fan on it rather than the required minimum of 3. It's been like that since the thing was installed. The monitor was put on sometime in 2009. After they found some other fans, they put, instead of just 3, they put 4 more fans on just to make sure it's going to be cooled down. And the following day, you can see the impact it has. The top oil temperature certainly dropped a lot with the same load and ambient condition in the area, and the hotspot temperature is back down to 111 degrees C. So it did make a difference. And the result was winding temperatures 20 to 40 degrees C lower than the night before with similar temperatures. That's the benefit of monitoring, being able, when things go wrong, you're going to know about it. If you have the proper communication set up and the data going back to a place where people will have a program to do something about it. So that controls the cooling system, as I said. You look on the left-hand side, there's a water-cooled rectifier transformer, OTWF. There's gauges on it that control the cooling system or let you know when things begin to go wrong. Right-hand side, the same thing with the ONAN, ONAF, and ONAF type. So those gauges control the functioning of the cooling system. We call it a cooling control. So from a monitoring point of view, we can measure top oil temperature. We can measure the winding currents. We have fixed parameters. We want the set point for top oil temperature alarms and hotspot alarms and load current set points. They feed into what I call the monitor, and then inside there are certain rules. The output is when to turn on and off stage 1 cooling, when to turn on and off stage 2 cooling, control versus status discrepancy alarm. In other words, the monitor says, I've told stage 1 to turn on, and it didn't for whatever reason. That's an alarm condition. And generally, we find when that alarm comes up, it's an issue either with, generally speaking, with the breaker controlling the motors. Somebody was in doing maintenance, they left the breaker in the open position and didn't close it when they left the site. Simple things. Or the cooler bank malfunction, one or the other. Oops. So electronic temperature indicators like the one on the left is designed to replace that one on the right in that image, I call it the vintage winding temperature indicator, the electromechanical device. And you can see that on the condensation on the window of that thing has sprung a leak somewhere with the atmosphere. And it's only a matter of time before that begins to rust out, corrode the insides of it, eventually making it non-functional. The electronic unit on the left-hand side, it's in a cast aluminum enclosure, IP66, and it has the feature of, on the right-hand side, one ETM replacing up to 4 of those devices on a transformer, and the reduced amount of cabling. It's the simplest thing you can do to help extend the life of the transformer is to control the temperatures and control the cooling system and have an intelligent system to let you know when things begin to go wrong. And it evens out the wear on the motors. The left-hand side, you can see in the bottom, across the bottom there, that bar chart showing the coolers coming on and off in function of the top oil temperature and the load, and they're always coming on and off. On the right-hand side, you can even out the wear on the motors with intelligent cooling control, and the variation of the top oil temperature is only 5 degrees C rather than 15 degrees C, while the load fluctuates more than the left-hand side. That's the advantage of using some intelligence on site. With bushings, I said this is one of the second leading causes of failure of transformers are bushings. And that's after on-load tap changers. Now, if your transformer does not have an on-load tap changer, their bushings become the second leading cause of failures of transformers. And then another CIEEE guide on, again, looking at failures of bushings. It was noted by the people in the working group that 50% of the time when a bushing fails, it leads to a fire and a loss of the complete transformer. And that's a global thing. So bushing failures have that impact on the equipment it's installed on. Offline testing, which is how we would recommend, everybody understands you need to test these things periodically. Offline testing is not always performed due to the unavailability of the outage required. That happens more frequently than people like to acknowledge. The failure modes are well understood for different types of bushings. The OIP, or oil insulated paper type, which has been around for a long time now, like older than me, while the RIP, the newer type, resin impregnated paper type, have a very different failure mode than OIP. And it's important to understand the failure modes and the time to failure of these two different types of bushings. They both do the same job. RIP have the advantage is that there's no oil. We call it a dry type bushing. There's no oil inside the bushing. It uses resin as the insulator around the condenser. It allows now, if you're monitoring full time on these, it allows to move from time-based maintenance regime and testing to a condition-based maintenance regime, on particularly related to bushings that need an outage to be tested. So it looks like this. It's that bushing you have on the bushings in IEEE, anything greater than 69 kV have to have that bushing tap that you see there. That's the test tap, as it's commonly called. That's the tap we use where it connects a sensor in there, and it measures the leakage current when the transformer is in operation. It also has the capability to detect partial discharge inside that bushing or inside the whole transformer. And there's many, now internationally, if you had bushings that are made to the IEC standard, there are, known to us, about 55 different types and dimensions of that tap. In IEEE, it's standardized on one dimensional, as you can see here, but the other ones, it makes for an understanding of the bushing condition, bushing type determines the sensor fitting. The sensor is the same. So it's been done this. It's good protection of the bushing, and it has to be robust and watertight, and no danger of open circuit when installed correctly. That's the important thing. So you have a three-phase transformer, and you basically put the sensors into all three phases on the high voltage side, and on the low voltage side, if there's taps there, we're measuring the leakage current, and leakage current will be different between different bushings. That's just a natural phenomena. The signals come into a balancing unit, what we call it, and the summation unit, where the monitor takes all three different currents and basically brings it down, calculates out a null position. So it's got looked at as a null meter. And out of that, we track then the sum, the vector sum of the three currents. And it can appear, as you see on the right-hand side, that polar plot. So you have a polar plot. This is the software that comes with the monitor. You can look at the polar plot trend or XY plot across the bottom. On this transformer, this was a transformer with older type OIP bushings where there were no further replacements for them. So they had to go out and get other bushings. In the fall of 2010, the monitored bushing began to trend past the 3% caution warning, which is the yellow circle. And beyond then the red circle, which is, hurry up and get there, you got a real problem. And when they go out, the first step is to arrange an outage and show the people and say, hey, this bushing is going to go bad if you don't give me an outage to confirm it. And in this case, they got the outage and they tested the bushing, and it tested out to 2.13% power factor, which is like over twice the amount of allowable power factor on that bushing. So all of the blue dots you see in that polar plot is an indication of a a record of the condition of the bushing. And the plots that is plotting one phase. And the bottom one is comparing in the blue dots of the measured power factor, relative power factor, compared to the top oil temperature of the transformer. And we all know that temperature and power factor there's a direct relationship between the two. When things are good and normal, we expect to see across the bottom, the power factor does fluctuate, top oil temperature does fluctuate, but when you have excessive temperatures, the power factor increasing in time with the top oil temperature of the transformer. This is an early indication that the bushing is going bad. And that's the alarm time. That's the time to start the schedule. Where's my parts? Where's my people? Get an outage arranged, because we're going to have to go out and replace the bushing. And the polar plot identifies which phase is going wrong. That's OIP type bushings. And by the way, it can also detect partial discharge inside the bushing. Here's another case of a US utility, and this is out of 138 kV distribution substation. They put a monitor on this C50 on the transformer, and they're monitoring bushings and other things on the transformer for 2 years. And then one day they get an alarm, and you see that trend chart on the bottom there. The green line is the relative capacitance, and the blue line is the increasing leakage current off that particular tap. They saw this. We saw they hadn't seen this sort of situation before, and they phoned our engineers, and we all looked at the data. And the consensus was, you need to go out and check the bushing. We think there's a leaking bushing. So they did send a guy out with binoculars first, had a look. Yes, there's no oil in the reservoir at the top of the bushing, as you see. And by the way, on the side, looking at the picture on the left-hand side, the oil was leaking out of that bushing, and it was going down the side of the tank. That's what you see. So somewhere along the line, somebody recognized the leak and they put, I'll call it goop, around it trying to stop the leak. Didn't do the job. So ultimately, the bushing had to be replaced. You can't fix that. So this is a case where stuff happens anytime after to a bushing in this case. And it's the case of being able to go out and identify there is a problem, go out and fix it, other than waiting for the time period to expire, so to speak, 4 or 5 years between testing. They may have had earlier warning had this bushing failed and taken the transformer with it. So that's the advantage of looking at OIP type bushings. And the one on the left we just talked about. The one on the right-hand side is the failure of an RIP bushing, a resin impregnated bushing. So it's a totally different insulation system around the condenser core and the bushing. Still, we can still measure the leakage currents. That doesn't change. It's still giving a value of relative capacitance and relative dissipation factor. And here you can see on this case, the yellow line represents the leakage current from one bushing. The bottom line is blue. That's the sum current of all three. But at some point in time, it begins to increase and it just starts increasing. The end result here is that the capacitance, in other words, the magnitude of leakage current increased dramatically over 1 hour. It increased the capacitance, and that's pure measurement of capacitance. It increased 85% in 1 hour. The bushing did fail. I mean, this is a failed bushing. This is how RIP bushings fail. It's rather quick. And it's all a function of there's probably a small void from when it was manufactured, and and eventually the breakdown starts and it starts to short out the condenser layers, and that's what you see here, increasing capacitance current, increasing leakage current. The benefit here is that the bushing, so much the bushing failed, but that it failed in a controlled condition, that there was no explosion. There was no shrapnel going across the substation yard because there's no oil in that bushing. So it's impervious to moisture coming in from the outside. That's the other benefit you have here of using this type of bushing. And that transformer was replaced with an RIP bushing. This case here is a different transformer. So they do fail. The other thing I remember from an IEEE meeting on bushings is that this is on a 230 kV bushing, overheating of the top terminal due to an improper connection of the connector to the terminal stud at the top. It overheated. The one, and I remember this from the bushing expert of ABB and Alamo, was telling a bunch of us at a transformer committee meeting, there's one thing about RIP bushings. Do not overload it. There's no overloading capability with an RIP bushing. And his exact words were, if the nameplate says it's rated for 800 amps, that's what it means. Not 801, not 802, 800 amps max. This is what happens if it's overheated. In this case, it was a bad connection on top, over temperature on the connector at the top, and it cracked. You can see across the top this epoxy insulator, but this was not porcelain. And you can see the brown goop. That's what I call it. That's the resin that has melted. It's so hot, the resin melted and started to come out. So note, RIP bushings should not be overloaded. That's the condition here. Moving on to this other thing that can fail, because it's one of the few mechanical moving devices on the transformer, is the on-load tap changer. So the benefit here, the benefit of the application of this is to control the voltage of going out of the transformer onto the network. There's different systems involved. There's the energy storage system. It's either a direct drive or a spring-driven type of mechanism. There's electrical properties we can record, counter for each tap. We can count how many operations have occurred at each tap. We can look at the contact wear, the I²T for each tap, and also understand the reversing switch operation. They've been known to here's the thing, tap changers have been known to fail shortly after some maintenance has been carried out. That's, I won't call it wives' tale, but that's, a lot of people say that's a fact of life. So on the distribution side of things in North America, we see a lot of this type of tap changer, that external compartment type. There's oil inside of that, but that's oil is separated. It's not, it does not touch the oil inside the main part of the tank. It's external. So you have a separate oil body. In this case, you have the motor operator down below, and that's when the tap changer is commanded to operate. Is told to, okay, go change taps now. Motor operates or a spring operates and moves to the next tap. The beauty here is that you can see here on the, I point out the magnetically held temperature sensor on the outside. There's one on the main tank as well. The beauty of doing this is that we can detect a lot of problems by looking at the temperature difference between the oil in the tap changer compartment and the oil in the main tank. The theory is the oil temperature in the tap changer compartment should be much less than temperature in the tank because there's really no heat source in the tap changer compartment. So by comparing the difference between the two temperatures gives us an indication that everything is good. Or if there's a problem in high side here due to some contact problems, overheating of contacts, misalignment of contacts causing that overheating, that's when the oil temperature will begin to increase inside the tap changer to be greater than the temperature in the tank. That's when your problem is discovered. So the model is from the same monitor that you saw before. Measure the tap changer temperature, measure the top oil temperature. It computes a rolling 24-hour temperature differential of values over time and tells you when things begin to go wrong. And this is what we're looking to detect. Left-hand side, that's a condition that was caught with this method. You can see the worn stationary contact in this case, and the black stuff you see is coke. That is what develops on the contact. It becomes then a much higher resistance contact, which just makes the whole temperature situation take off, so to speak. And on the right-hand side is what you see after fixing a stationary contact in a good condition, where you can see there's no excessive wear on that. That one on the left-hand side has the potential to go open circuit if left undetected, and that's what you don't want to see on a transformer. You can track now the number of tap changes per tap over time. And you can set alarms on making sure your tap changer isn't going to run away on you. You can set it to alarm on the maximum number of tap changes you expect per day as an indication. I won't spend a lot of time on dissolved gases other than strategy that people can use when using dissolved gas monitors to look when things start to go bad with the active part inside. Because oil is in contact with every component of the active part. If a fault occurs somewhere inside that tank, it will begin to degrade the oil in the area of the fault and gases will be generated. A sudden increase in dissolved gas levels is the best indicator of a developing incipient fault related to the core and the windings that make it up. So many people have decided, I want to do multi-gas, which is fine on really critical transformers like generator step-up transformers at a nuke plant, for instance. That's a very critical transformer, generating station application. But if you're out and at a steel mill that needs, that's feeding an electric arc furnace, that's probably another place for having a multi-gas monitor on the transformer. It's critical to the production of steel. Without the arc furnace working well, because the transformer's not working, your production goes to zero. And now it goes back to what I was saying, 90% of the time, things are working well. 10% of the time is when you need to have some early alarm that things going wrong. And that's when people are using a hydrogen specific or hydrogen and carbon monoxide specific simple sensor plus moisture sensor to understand and when things begin to go wrong, because hydrogen was one of the earliest gases produced in this whole temperature cycle. So this is taken from C57104, 2019, the latest edition. And this chart is meant to represent the generation of these different gases produced in the oil of mineral oil of a transformer. So it starts down in the lower levels of partial discharge. We have cold plasma or catalytic things going on. It's not related to temperature. So I think we call it stray gassing is another word for it. But as the temperature of the fault increases, you see the rate of production of hydrogen drops off to be overtaken by methane, ethylene, and ethane. And acetylene is out the right-hand side, the indication of discharges arcing inside the transformer, and hydrogen takes off as well at the same time. So hydrogen is, we call it the early indicator of when things begin to go wrong. So these simple sensors of hydrogen are combined with carbon monoxide. Don't forget moisture, act like a smoke alarm in your house. It's there to tell you when things go from good to bad inside your house or factory or shop or store, or whatever, from normal to abnormal, as I call it. And when it triggers off that, hey, I see this other gas is coming on now, it's not there before, it's abnormal, it triggers the alarm. That's the time to go out and start to pay attention to that transformer of taking oil samples, depending on the results, trying to define what kind of a fault's going on and taking action there. So people would do that on a chosen fleet or chosen population of transformer, put the smoke alarm on and have ready one or two multi-gas monitors that can be put in place to monitor intensely. It's like going to the hospital and being on a heart monitor to monitor intensely the condition of the transformer as it relates to gassing and trying to control the gassing rate, which may be controllable by reducing the load. Here's a simple gas monitor. This one hydrogen only. And it's on a new one when this was found. So this is what we expect. You start out with basically no gas. That's the norm. But in this case, over the first 2 or 3 months, it's increasing slowly. This is normal. But at some point, it takes off like a rocket. The rate of the gas concentration takes off. And the alarm goes and they go to take the sample of oil and determine there's a bad fault inside. And it turns out it was related to the core. This was on a brand new transformer. So they caught the problem early. It was an incipient fault developing after some initial loading, and it was still in the warranty period. So gas monitors at times provide the evidence that a fault was present because you have now the data record of when things began to go wrong. And there's no arguing the fact that when this happens, something is going wrong and take action to do it. Monitoring can also have the impact of maintenance reductions over time. When you look at the winding temperature indicators with frequency of going out and writing down the number was monthly in the number of cases. Frequency with monitoring, provided you send this information back to, because the information is stored on the monitor and communicated back to monitoring center or to SCADA. You don't need to go and do that monthly. There's no, because it's monitored continuously. The cooler inspection, yearly, now it's condition-based. It's only when the monitor says, I'm detecting some problems with these coolers, not as many fans are running as should be, for instance. That's a condition that can be detected by the electronic temperature monitor. And going back to DGA, somebody may be monitoring frequency of monitoring, when I say that, taking samples every 6 months. It could extend out to yearly, but the technique is this key gas monitoring with moisture, and when necessary, bring in the heavy artillery of the multi-gas monitor. Same way for the tap changer, external type tap changers using that temperature differential situation. Bushings, frequency, normal with no online monitoring is 4 years. That's normal, I'll call it normal frequency. If you put those bushing monitors on there, now you can extend that period of confirming that the bushing is good every 8 years. And periodic LTC inspection frequency is 5 years. If you're monitoring it, done. It's on condition, or as the OEM, as the tap changer specifies. And electrical testing can follow the same thing. Every 4 years, you would want to go and do some electrical testing on the transformer by looking at the DGA and the bushings. They're looking at key gas DGA, harmonics, fault counting. There are systems there that can now count the number of faults and how much and for how long that fault was there. You can push it out to perhaps 8 years. The visual and thermal inspection that was being talked about before, the presenters before, it yearly. You can do it on condition when you see a bushing going bad. Okay, send somebody out with the visual and the thermal cameras to go and take pictures or view what's going on. One of the more common failure modes of a bushing is that top terminal at the top of the bushing, especially if it gets hot. Deterioration of the gasket at the top of that bushing, like terminal. If it deteriorates to the point where it's not sealed, moisture, even the moisture from the ambient, doesn't have to be rain. Moisture from the ambient comes inside, goes into the oil and the bushing. Oil and water don't mix. We all know that. The water goes into the paper of the bushing on the oil OIP type bushings. So the question was asked before, if I only do this, is that going to help me extend the life of my transformer? Like if I only do DGA, is it going to extend the life of my transformer? I say, well, it's going to keep an eye on the active part, but it's not going to tell you things about bushings. It's not going to tell you anything about cooling system. So it's a combination of these things that can give you that overall picture of how things are going. So leads me to my last slide here, alarms. And what do we do? And I stress, asset monitoring is not a set it and forget it activity. I've seen too many cases of this where people think, oh, my problem solved, that's done, it's connected and alarms go somewhere. Maybe not. I've seen people install it, but the alarm setting is the responsibility of another department. It never got done. So the monitor's alarming. In the case, one case I know about bushings, the monitor was saying something's wrong, something's wrong, something's wrong. The relay contact changed state. It wasn't connected to any device inside the substation house. The bushing failed, took the transformer with it, all because nobody finished the job of connecting it to the RTU. And even after that, nobody had training about what that white box on the side of that transformer is all about. So it's important. You have to have the set. You just don't set it and forget it, is what I'm trying to say. Responding to a warning too slowly or ignoring an alarm, I've seen that happen, can turn a very simple maintenance issue into a significantly more expensive problem. An alert that goes unheeded is not a technology problem, but rather an issue of execution. Therefore, it's crucial to formulate the response plan when monitoring technology is being installed. Having monitoring technology is the first step, the correct first step. Second step, training for everyone that will be involved. That goes to the field people, the substation people, operating people, the maintenance people, systems operations people. Train everybody to have them understand what this whole new set of data and this whole new set of alarms means, and have in place what you're going to do and who is going to do it when an alarm comes in. That's the very vital piece. So as an example on alarm statements, this is an example where you may have an alarm condition of top oil temperature and loading is above the maximum rating of the transformer. The diagnosis is the transformer is currently operating at a temperature above the first alarm level. It's apparently caused by high load currently applied. The prognostic, here's what's going to happen if you choose to ignore this alarm. In other words, if this condition is maintained for several weeks, it could result in accelerated oil aging and certainly paper degradation. The recommendations are make sure the cooling system's operating right. Check the ambient temperature. Is it make reality with temperature alarm, and evaluate the acceptable load with regard to the ambient temperature, and likewise consider reducing the load. There may be others. This is a function of the people running the transformer. So a quick recap. There's benefits for new technology, the valuable tool for condition assessment and understanding when things begin to go wrong. And also when things go wrong, how can I keep this thing in service long enough? By what do I need to do to keep it in service until I can get a new one in place, especially these days where I just did a survey with some OEMs in North America here. The fastest lead time is 4 years. 4 years. You gotta, and hoping, somebody's going to say, well, I hope my thing, lasts that long. Hope is not a strategy. You have to put something in place to make certain that your critical assets are going to be watched.